Okay, so let's talk about what BFS actually means. And BFS gives you the distance from the start node to any other vertices in the graph. So how do we do that? Well, let's say we start out and we say that the distance from the start node to any other vertices is infinite, i.e., we don't know the distance. We don't know the distance yet, and of course, we have to set a base case where the distance from the start node to itself is zero. Okay. Now, what we could do is collect some data while we're traversing the graph. And namely, we'll say that the distance to any variable, to any vertex, sorry, is simply the distance from the start node to its parent plus 1. Okay? So, what does this do? In undirected graphs, we have a particular start node here. There we go. We have a particular start node 1. So that has a distance of 0. And next we have next we go and explore 2 and 3, right? And each of 2 and 3 the distance to 2 is equal to the distance of s, which is 0, plus 1. So the distance of 2 is going to be simply 1. And the distance to 3 is going to be 1 by the same logic. Okay. So we reach a point where we start exploring 4, and the distance to 4 is simply going to be the distance to 2 plus 1. So the distance to 2 is 1, then we add 1 to it, so the distance to 4 from the start node is simply 2. So we color that in. And this will be, the logic will be the same for all the vertices. 4, 5, 7, 8. And finally, we have 6, which is the furthest away from the start node in terms of edges, number of edges you have to traverse to get there. Okay, so what the BFS algorithm is doing is effectively layering the graph. It's grouping the vertices in groups according to their distance from the start node. So the properties for BFS in a undirected graph are simply that the search tree contains exactly the set of vertices in the connected component of S. That's pretty self-explanatory. That was true for the explore algorithm as well. And then we know that if the distance to U is less than the distance to V, then U is visited before V. That is pretty self-explanatory. And that for every vertex U, the distance to U is the length of the shortest path in terms of number of edges from S to U. Okay, that makes sense to you hopefully as well. Simply because since we are exploring these vertices as a queue, then there will be never the case where 3 gets explored because of 2, right? 3 is always explored, a vertex is always explored by the parent that is closest to the start vertex, right? The parent that's closest to the start vertex will always put its adjacent neighbors on the to explore queue first. Okay, so 2 wouldn't put 3 on the to explore queue. 1 puts 3 on the explore queue. And that's very important. Also, if U and V are in the connected component of S, and there is an edge between U and V, then the distance between U and V is less than or equal to 1. Okay, that's pretty self-explanatory also, right? If I don't know what that was. If we have a node U and we have a node V, and then something S here, and then we go through, get to V, and we have an edge U to V, then of course, the distance between the maximum distance between U to V is 1, right? The maximum difference between U and V is 1. And that's not, that arrow shouldn't be there. It's an undirected graph. Of course that's true, right? There can't be a case where U does not add V to the Explorer list and then V gets added to the Explorer list by something that's further out, like T, and adds U, right? That doesn't make any sense. U has to be, if U Yeah, the distance between u and v has to be no greater than 1. Okay. So we could also look at BFS for directed graphs. And again, we see that the BFS breaks directed graphs into layers in much the same way as it did for undirected graphs. So if we start at A, this is distance 0, then we could go to the adjacent neighbors to A. These nodes here would be simply distance of 1. This is distance of 1. Then there is the nodes adjacent to those would be the distance of 2. Distance of 2. And finally, we have one node that is 3 edges away from the start vertex from A. Okay, so exactly the same algorithm as we saw before, but now it's in the directed case. Now, the directed case properties are slightly different than the undirected case. So we still have the properties where the search tree contains exactly the set of vertices reachable from S, but this is a slightly different task, right? This is reachable from S. In the undirected case, this was connected to S. So reach and connectivity are different things. And so in the directed case, we have this concept of reach, as we explained before. And so this property changes slightly, although its spirit remains the same. And then we say property B is the same, that if the distance to U is less than the distance to V, then U is visited before V. That's self-explanatory. And for every vertex U, the distance to U is the length of the shortest path from S to U in terms of number of edges. All that is exactly the same as the undirected case. The one thing that is different is that if U is reachable from S and there is an edge UV, then the distance of V minus the distance of U is less than or equal to 1. But it's not necessarily the case that the distance of U minus the distance of V is less than or equal to 1. Okay? And why that is simply imagine the graph. Imagine we have a S here, and we have a path with lots of vertices to U. And then we have a path with few vertices to V, and we have an edge from U to V. Okay? So the distance to V, the distance to U could be far, far greater than the distance to V. Right? It's not that the simple point is that just because you have an edge here doesn't mean the distance of V has to be 1 away from the distance of U. That's all that means. Okay. Great. Okay, so if you're going to mark layers for the BFS algorithm, this is the algorithm, this is the way to do that. Simply, we mark all the vertices as unvisited and initialize the tree to be empty. And we mark S as visited, and we add S to the toExplore queue. And then we say we add S to the 0 layer. And we say while the next layer is not empty, initialize another layer to be an empty list. And then for each U and Li, simply add the vertices that are adjacent to the current layer to the next layer, to Li plus 1. Okay, so that's another way to do BFS, except grouping the vertices into layers. And this, of course, runs in linear time as well. Okay, so last couple properties. BFS layers is outputs a breadth first search tree, and each layer is the set of vertices that are at distance exactly I from the start vertex S. And if the graph is undirected and each edge UV is one of three types: a tree edge, which is between two consecutive layers; a non-tree forward or backward edge between two consecutive layers; or a non-tree cross edge with both U and V in the same layer. Okay? And so every edge in the graph is either between two vertices that are in either I in the same layer or in two consecutive layers. Okay, and why is that? Because because the case where S, let's say we have a layer 1, a layer 2, and a layer 3, it is impossible to have an edge that goes from one layer to a non-consecutive layer, right? Because if there was such an edge, like this, then this node should be in this layer, right? So you can prove this very easily by contradiction. Okay, and also talking about layers. For the case where G is directed, where the graph is directed, then every edge is one of four types: the tree edge between consecutive layers, a non-tree forward edge between consecutive layers, a non-tree backward edge that is not necessarily between consecutive layers, or a cross edge with both vertices in the same layer. Okay, so the difference is for directed graphs, you could have backward edges that are not necessarily in the same layer. All right, and hopefully that makes sense, simply because, again, we could draw the graph out real quick. S, V1, V2, V3, back to V1. Simple as that, right? Okay, so now that we got that down, let's talk about shortest path algorithm next. Stay tuned.